So please join me in welcoming Carl Wyman and Eric Cornell.
Okay, so laser pointers out. There's the, yeah, okay. Thank you. This is all about getting things very, very cold. And so I want to start here by reminding everyone what temperature is all about. And I'll play with this. Eric, why don't you explain what I'm doing here?
So what's going on here is the particles are zooming round and round, and everything, as we know, whether it's gas or atoms or apples or whatever, everything is made up of atoms. And when the things are hot, the atoms that make them up go very fast. And as they get colder and colder, the atoms that make things up go slower and slower. And so this is a pretend gas here. So we're pretending we can look in and take a movie of the atoms zooming around inside this gas, and you can see this gas has come all the way to a stop. What's the significance of that, Carl?
So when things come to a stop, that's clearly the coldest you can ever be. And so that's what we call absolute zero. And so the whole point of this is to work way, way down here at the bottom, which is, it's minus 460 degrees Fahrenheit. So extremely cold, where basically all this atomic motion stops. Now, one of the things that's really interesting is that we do a whole lot better than nature does. Here is the coldest nature can get. It's up at about 3 degrees above absolute zero. And we have to get millions of times colder than that. And so we like to talk about our laboratory as the coldest spot in the universe. And it may well be.
With good reason. On the other hand, there is always the possibility that the Alien Science Foundation has funded similar research on some other universe, but all we can do is speculate.
But when you go past that tall, skinny building over there of Chilla, you can nudge your neighbor and point out that that's probably the coldest spot in the universe there.
Certainly on Earth.
Now, okay, but we aren't in this just to set records for low temperature. So Eric, why do we do this?
Why indeed? Turns out that as atoms move slower and slower, okay, we explained getting colder means moving slower and slower, they turn more and more into waves. The very important physical idea of quantum mechanics tells us that everything is both a particle and a wave. It's one of these little contradictions we come to live with in physics. But it really is the case that as things get colder and colder, their wavy nature becomes more and more significant until, in fact, you can really think of this Bose-Einstein condensation that we realize as the ultimate triumph of waviness over particleness.
Yeah, and it was really Einstein way back in 1924 predicted that as you got things cold, they would very suddenly, all these atoms would jump into the lowest possible energy they could have and all coalesce into this super cold giant quantum wave. Now, nobody took it very seriously when Einstein first predicted this, including Einstein, because this was sort of ridiculously low temperatures. And because it turns out you have to get down to something like 100 billionths of a degree above absolute zero. Now, even up to very recently, when we started pursuing this in 1990, at that point, the temperatures that it was clear one had to get to were vastly colder than what scientists had been able to produce over the last century of trying to cool things more and more. But so that was really the goal we had set out for ourselves. But as Eric will explain, it really wasn't as easy as it sounds.
Right, let's go back up one more time.
Sorry.
We need to get the atom so cold. This little fuzzy ball here represents an atom which has gotten so cold it's kind of turned into a fuzzy wave. You need to get the atoms so cold and so close together that the fuzziness of one atom overlaps with the fuzziness of another atom. And I've made a little plot here, so hang with me. There's not a lot of math in this talk, but over here I got temperature, and over here I got density. You need to get the atoms cold and dense to get into the BEC zone. Otherwise, you're in the non-BEC zone. So, Carl, could we zap along here? Now, what I want to emphasize is that there's something, in some sense, wrong about making Bose-Einstein condensation. Here's another plot. This is called a thermodynamical phase diagram. Basically, it applies to everything. Everything, when it's hot at high temperature and at low density, it's a gas. When it's cold and at high density, it's a solid. Somewhere in between, it's a liquid. But all around here, there's a huge zone which is forbidden. You can't go there. Why? Because it's forbidden. Suppose, you might think, okay, but you suppose you're the sort of naughty person who wants to go in the forbidden places, and you say that little purple X up there, that corresponds to water at, 20 degrees Celsius, room temperature, and say a tenth of the normal density of water. You say, what's to stop me from doing that? I'm going to take a quart jar of water, and quart jar bottle, I'm going to fill it 1/10 of the way full of water, I'm going to screw the top back on, and now I've got something which is 10% of the normal density of water and at room temperature. But it's not really like that. There's no place in there which is at that sort of forbidden zone. At the bottom of the jar, you've got water, which is at its full density of a gram per centimeter. And at the top of the jar, you've got gas. But nowhere in between do you have any of this stuff in the forbidden zone. Why? Because it's forbidden. So let's see one more slide, and I'll show you what this comes together. We put the two slides together. You see that Bose-Einstein condensation is truly a forbidden science. To get into this region where you can make a Bose-Einstein condensation, you have to get cold enough and dense enough that you're in this forbidden zone unless you're way up here where you're a solid. And the rules are solids can't Bose-condense. So really, we're not really allowed to make a Bose-Einstein condensation. It should be impossible, except, and this is the beauty of being at a major university instead of at some federal research lab. Here around us, we have not only scientists, but also we have liberal arts majors, theologists, things like that. And one of the things you learn in theology is that the things that are truly impossible to do, they don't bother to forbid. So the fact that this is forbidden should be encouraging to us. Moreover, on the second day of that theology class, they told you they don't bother to forbid it unless it's also kind of fun, right? It's not. So now we have both encouragement and motivation to proceed.
So, in fact, what we really have to do is kind of trick these atoms into getting way into the forbidden zone and not turning into a solid like they think they're supposed to be.
And that basically involves keeping the gas not very dense and getting it extraordinarily cold.
Yeah.
We keep coming back to that cold. And how do we get it that cold anyway?
So we do this basically, the heart of it is a pretty simple looking apparatus. Little glass cell here, you pump out all the air, you put in a few of the rubidium, it's the kind of atoms we want to cool down, they're bouncing around inside here, and we've got laser beams that we send into this, and we've got blue and green things, and blue and green things are coils of wire that we can run electric currents through to make magnetic fields. And so, oops, I'm never supposed to show this slide with Eric on the stage. Oh, no, I'm all right. It's centimeters, I guess. So,
yeah, that's right.
yeah,
2.54 centimeters.
See, when I give the talk, it's inches, but he's a federal National Institute of Standards and Technology employee. You can't use that. Okay, so let's go on to show you how we use this stuff. Oh, no, first we'll show that the artist's conception is a little neater than the real thing. It's the glass cells buried somewhere down in here.
There's those magnetic coils you saw before, and there's actually the glass cell, which is 2.54 centimeters across.
Right. Now, this whole thing sits on a table.
About twice as big as this table right here.
And these kind of experiments, I mean, we credited the graduate students and postdocs because they really do build this. This whole thing is put together by them, made work. Here's a couple of Neil Clausen, Sarah Thompson, Liz Donnelly working in the lab. The other thing, hidden behind the wires there.
Oh, okay, good.
The other thing you might come away from this picture with is the realization that the Nobel Prize Committee doesn't give any points for neatness. Okay, so on to the first step of cooling, which is shining laser light onto the atoms and actually slowing them down. And you want to explain this?
When photons not only carry energy, the things that make up light, which is photons, They not only carry energy, they can carry momentum. When you step out into a bright sunshine, you feel a push from the sunshine beam that blasts you back into the door. It's actually a very, very small push. Most of us aren't even aware of the fact that sunshine applies a push to us, but of course it is that push which is behind the secret of the soon-to-be Olympic sport of solar yachting, right? Space yachting. But it is a small force, not so much because the force is small, but because we as people are big. Atoms, in contrast, are small, and the force that photons, you can see this laser here is actually shooting photons out.
Yeah,
The force
photons are little particles of light, we should say, and lasers allow you to put out many, many photons.
And the effects of those photons bouncing off of an atom, represented here by a little gray ball coming in from the side, is actually quite significant. Here you can see Carl is blasting the ball back with its... Scaled down, it turns out that the force from light pushing on an atom is strong enough to apply accelerations 10,000 times the acceleration of gravity. So it's not a small effect by any means.
Okay, but just pushing them around, of course, isn't good enough. You got to slow them down no matter what direction they're moving. And so in the middle of that glass cell, so picture this as that little glass cell. And
Here are the laser beams coming in from the north, the south, the east, and west, and there's ones you can't see coming in up and down.
Right. And these are supposed to be rubidium atoms. Of course, they're much bigger and much slower than the real ones. But now what's really important is how the color of the laser light is. So if I go up here and I'm a little green, you want to explain what's going on while I
As
adjust
the atoms come through, you can see they actually speed up. This is definitely getting it wrong. You don't want to have the laser light a little bit too green. You want to have the laser light a little bit too red compared to the favorite color. As you know, atoms all have a favorite color. Sodium is yellow because sodium is the boring yellow color you see in parking lot lights. Rubidium prefers a sort of brick red. And it's when you hit right on that favorite color that you can slow them down most efficiently.
Well, no,
Not
slightly to the red of the favorite color.
Good point.
He's been lecturing too much, been out of the lab. So,
That's true.
Yeah, and those are the basic reason for this we won't get into, but it's, if you're familiar with the Doppler shift, you know that as the atoms move because of something called the Doppler shift, they see the light at a little different color, whether it's opposing their motion or coming from behind. And
you can really see here why it's called optical molasses. These things are getting stuck like flies on molasses.
right. And so after a few seconds, in the middle of that cell where the laser beams are, if they're just the right color, then you get a bunch of atoms piled up inside there. Now, we first did this back in the late 80s, and we were all excited because we got things really cold. But very quickly, we started asking ourselves, why can't we get them any colder? And we realized there are several processes, but you can actually see the most important one, which is these atoms in here are basically lights bouncing off them all the time, and it's bouncing back and forth between the other cold atoms piled up. And so if you look very carefully, you can still see these are jiggling around a little bit because of those little photons bouncing off them. So we'll get rid of the photons.
What happens then? They fall. Gravity is not a very big effect to the air in front of you, which is, the air in front of the atoms here is at room temperature. These atoms are going hundreds of miles per hour. They can't be bothered with gravity. But the atoms that we've slowed down using laser cooling, gravity is a pretty big force to them, and they just fall down to the bottom of our glass cell and stick there. That's the end of them. We have to figure out something to keep them from falling down, and we do that by turning on a magnetic field. The atoms that we use, rubidium atoms, they're like little bar magnets. Each one's got electrons spinning around, and it's like the little bar magnet that sticks on your refrigerator. And you can apply a force to that by turning on a magnetic field.
Yeah, the green and blue things that I talked about way back at the beginning are coils of wire. And so now that we've turned the lasers off, we turn the current on through those wires, and that makes the magnetic field Eric's talking about.
We think of the atoms as sitting in a little bowl, but there's not really any physical bowl there. It's just sort of the shape of the magnetic field that keeps the atoms all stuck here, as if they were in a sort of a curved bottom bowl here.
So what you need to picture is that we have in the middle of a little glass cell a little cloud of atoms floating there, held extremely gently by nothing but magnetic fields. And this is great because they don't heat up, and then we can do other stuff with them.
The nice thing about magnetic trapping is they have built into it a very natural form of cooling called evaporative cooling, which is the oldest form of cooling known to man. Here we have a cup of coffee, and you can see the steam coming off of it. And of course, when the very first cave woman was sitting around the fire with her cup of cave coffee, watching the steam coming up from it, that was evaporative cooling. Her coffee was cooling off, and it's really the same technology updated for the 21st century.
Right. So just like in the coffee, when we dump these things into a magnetic bowl, the ones with the most energy to escape out of the bowl take away more than their share of the energy. And so the ones that are left behind get colder. But that doesn't happen for very long. You know your coffee doesn't usually get to absolute zero. And it's because in our magnetic bowl, for the same reason, after a little while, no atom's got enough energy to escape. And so while I try and make the experiment work, Eric can explain to you.
I don't want to drown you in the technical jargon, but in coffee it's called the work function, the coffee work function. There aren't enough atoms left to sort of break free of the coffee. Here, we can lower the edges of this magnetic bowl, and we keep getting them lower and lower. The atoms zoom around, and we always set it up so there's always at least a chance for one of the atoms. See, there goes one, there goes another one. Each of these atoms are making a break for freedom and taking with them more than their fair share of energy. You can see the remaining ones cool down. There's the temperature of the ones that are remaining. They're cooling down, and that's the target temperature where Bose condensation happens. And you can see that the atoms are catching up with this. And if Carl's very good, he can sometimes have as many as 20 atoms remaining.
Yeah, and just in this video game, it's exactly like in the experiment, in that you go too fast, you lose all the atoms, you go too slow, they don't get cold enough, and it takes about a minute of slowly bringing this down, and I got to concentrate more if I'm going to get a decent score.
Whoa, yeah.
Not great. Okay. Okay, so the real Bose condensate doesn't look like that, a little pulsing blob. So now let's talk about what it does look like. Let me find, okay, here.
This is how we take a picture of the atoms. Basically, the way we study these things is by taking pictures. There's not very many things you can do to them. Only the atoms get cold. The glass itself is warm. The magnetic coils are warm. Everything else in the lab is warm. You can't just take a thermometer and touch the atoms with the tip of your thermometer, because the thermometer itself is going to be much, much hotter than the atoms, cause them to boil away. Basically, the only thing we can do to them is take pictures of it. There's a cloud of atoms. We pass a laser beam through the atoms, and the atoms absorb some of the light. Now there's a shadow in the laser beam, and that shadow falls on a TV camera, and where the shadow is dark, that corresponds to where the atoms are dense. And if the shadow is big, that means we've got a big cloud, and we can learn the things we need to know about the atoms using these pictures.
But of course, the real data is just little black and white shadow pictures, but we all know that you don't get attention with black and white anymore. So we dress this up when we present the data. And here's actually our first data showing Bose-Einstein condensation, and this could well be the most famous physics data in existence now. This is on
June 1995.
Right. June 4th, right? This is in every textbook. It's on covers of textbooks, you know, T-shirts, calendars, and so on. Okay.
Mouse pads.
Yeah, mouse. So what this is showing is 3 different images here that are getting the sample colder, sequentially colder and colder and colder.
The first sample here is for us the relatively balmy temperature of only 400 billionths of a degree above absolute zero. And if you look at the shape of the cloud here, it's smooth. You've got sort of atoms of all different energy all participating. It looks kind of normal.
So why don't you keep going ahead?
You get a little bit colder yet, and into the middle of the sample, you see forming the nascent Bose-Einstein condensate. That right there, that corresponds to about 3,000 or 4,000 atoms all participating in the very low energy wave that sits there in the middle. And this bump here is exactly this wave we were talking about that all the atoms form.
Yeah. So in terms of the shadow, the big peak corresponds to a very dark shadow. In terms of the atoms, they correspond to a very dark, a very dense little blob that's not spreading out at all like normal atoms. And so we'll give you show you sort of an analogy.
Oh, okay. So imagine, I should tell you that when we take the pictures of these atoms, it destroys them, and then we have to start fresh. So although it looks sort of as if we have sort of a sequence of atoms getting colder, 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 really what we do is we make one pot of atoms, we let them sit there. After a while, we look, and those aren't condensed. What does the not condensed atoms look like?
So, yeah,
Oh,
so
that was
we
very
dump it out,
disappointing.
splatter all over the place.
See, this is why you get to sit in the front row. This is where all the excitement is. Next, he's going to smash a
Yeah.
watermelon with a
So
sledgehammer.
now we go. Now we go run our experiment again.
This time we let the same thing, a similar pot of atoms, but we let it sit in the freezer, so to speak, a little bit longer.
And so it's colder. And now when we dump it out,
There's this one little hard thing here, and God, that's cold. The condensate, there it is, folks. So
yeah. So
that's the little lump there in the middle, the ice cube in the middle. If we kept get it cooling further and further, you wouldn't have the steamy stuff. You'd just have sort of the ice cube, which is the condensate. Was that cold down there? I'm awfully sorry about that. The safety people are going to be all over us on this.
now, the real blob here is actually not nearly as dense as this block. It's a very dilute gas, but it's much denser than the other stuff around it.
Well, basically, we put together a little movie of the condensate forming. We took a whole series of images of the condensate, and here you can see the temperature coming down, and there's the target temperature, and right when the condensate, we pass the key temperature, the condensate forms, and that little blob there is the condensate with now thousands and thousands of atoms, and these days we have millions and millions of atoms all participating in this single quantum wave.
And so this is running faster than the real experiment. The real experiment, to take one of these samples and make one thing takes about a minute. Okay.
So, as we've emphasized before, we didn't actually do very much of the work. And we can't recognize all of the people who contributed, but here are 4 people who were around in 1995, Mike Anderson, Debbie Jin, who's currently on the faculty here, Mike Matthews, and Jason Ensher.
And yeah, this was quite recent after we'd gotten Bose condensation, and so you can see they were appropriately happy about the accomplishment. Except for Mike, who, if you know Mike, you know this is wild.
That's about as ecstatic as he ever looks.
He's completely ecstatic there.
So it's worth thinking a little bit about what the condensate's like. We said it's like a wave. What do we really mean about a wave? One thing we know about waves is that when waves overlap with each other, they interfere. They can interfere constructively or destructively. And Carl's going to do a little experiment here where he takes 2 condensates and runs them together, and we see bloop, weird patterns.
Yes.
What's the significance of those
So
patterns?
when you've what this is really saying is you've got one little blob of atoms in a gas, you put another little blob of atoms in a gas on top of it. Now, we do that in the atmosphere all the time. We've got nitrogen, oxygen all mixed up there, and we just got more gas. Here, when we put one little blob of condensate on top of another little blob of condensate, there's gaps there, and that gap means there are no atoms there. Now, that second blob of condensate didn't come and push those atoms away. It just convinced them that they really weren't there in the first place.
We're getting into the sort of twilight zone of quantum mechanics
Right.
here. I mean, you can see why we get excited about this stuff.
Yeah, I mean, this should seem totally bizarre and
Can we do that again, by the way?
Sure.
I never get tired of this.
Yeah.
Bloop.
Yeah. Don't come up and ask us to explain why this is. This is just quantum mechanics. That's the way it is, and it makes no sense. I mean, it's totally different from anything one experiences in normal life. And, it's just remarkable that that's the way it behaves. But
Get over it, is what he's saying.
Yeah. But the great thing about this is physicists have been studying quantum mechanics and know that deep down it's the origin of the explanation of everything, why atoms behave the way they do. But it's always been confined, deep inside the atom, tiny things you could only indirectly sense. These blobs, they're the size of a human hair. And so, That's
Carl
something-
means big in this
Yeah,
context.
you can see, right? It's a human scale, and that's really what's the source of why people have been so excited about this.
So boson-sign condensation in the years following 1995 became a growth industry. There have been thousands and thousands of papers published on it, and we can't possibly review for you all the different current experimental directions. In a little while, we're going to come back, sort of return to the science part of our talk and describe to you some of the interesting things that we're currently working on with condensate, some things we're most excited about.